কিরে সবাই চুপ কেন? শোনা যাচ্ছে না নাকি? এক মিনিট, শোনা যাচ্ছে? ভাই আমি শুনতে পাচ্ছি না কেন? এই যে এবার শোনা যাচ্ছে, হ্যাঁ। আমি শুনতে পাচ্ছিলাম না এতক্ষণ। আচ্ছা, so yesterday we stopped at cardinality of set. So we'll start from there. So, cardinality. What do we mean by the cardinality of a set? So suppose you have a set S having n elements a1, a2 up to an. Then we define cardinality as the number of elements in S. So in this case, the cardinality which we write with the modulo sign. So cardinality of the set in this case is n, because we have n elements. So take another set, suppose the set S x such that x is a perfect square and x is less than 120. So S is a set such that x is a perfect square and x is less than 120. So what is the cardinality of this set? Anyone?
What did you say? X is a perfect square and x is less than 12, right?
Less than 120.
Okay, I'm getting that 12.
Hello, Dada.
Yes.
Hello.
Well,
Dada, I had an exam. I just joined now. Can you tell what are you doing?
okay, we haven't started anything much yet. So basically we have started with cardinality where we stopped yesterday. So cardinality is basically the number of elements in a set. Yes, what?
What is the
10.
Yes, it's 10 in this case.
What is the question,
So
Dada?
the question is, so we have a set S over here. It consists of x such that x is a perfect square and x is less than 120. So how many? What is the cardinality of the set?
Because the maximum is 100, it will be 10.
Yes, it will be 10. So the idea of cardinality is hopefully clear to you guys. So suppose we have a set S, the cardinality of which is n. So what would be the cardinality of its power set? Anyone?
Power 2 to the power x.
2 to the power n, exactly. We did this many times. So the cardinality of the power set is 2 to the power n. Now we'll be in math we mostly deal with these sets. So we have
Which set, Dada?
R, we have Q, we have N, we have Z, we have C. So mostly in class 11 up to 12, we'll be dealing with these 5 sets, R, Q, N, Z, C. So what is R? R is the set of real numbers. R is the set of real numbers. So from minus infinity to infinity. Q is the set of rational numbers. So what is a rational number? Rational number is any number which you can write in P by Q form, where P and Q are both integers. What is a natural number? You know by now. 1, 2, 3 up to infinity. Z is the set of integers. So you have -2 as well, -2, -1, 0, 1, 2 up to infinity, and minus infinity over here as well. And complex numbers, you know, it includes real numbers plus stuff like 4 plus 2i, 5 plus 3i. And we also have irrational numbers,
I
but
said I means imaginary.
yes, iota, like if you have x square equal to -1. So this is the solution of this. And we also have irrational numbers, but we won't be dealing with them too much. So now let's look at the cardinality of these sets. Now, what would be the cardinality of the set of natural numbers?
Infinity?
Yes. Why?
Because they are infinite natural numbers.
Yes, exactly. So the cardinality of natural numbers is infinite because it has an infinite number of elements. Suppose the set of natural numbers is a finite set. So if the set of natural numbers is a finite set, it has a maximum element in it, suppose an. But we know that an plus 1 is a
And
natural
plus 1
number.
is also a natural number. That will be the maximum.
Yes.
That will contradict.
Yes.
So it's
So we have a
infinity.
contradiction. So it will be in n, and therefore we have a contradiction. So the set of natural numbers is infinite, as well as the other sets which we have discussed now, like real, complex numbers, etc. So now we'll introduce another term, which is countability. So what is countability of a set? If you have a finite set, it's simple, like 1, 2, 3, 4. This is a finite set, so it's countable. Any finite set is countable. But if you have an infinite set, we mostly use the term countability to refer to infinite sets. So if we say that a set is countably infinite,
Countably?
Infinite if there exists a bijection from a set S from N to S. So a set S is countably infinite if there exists a bijection from the set of natural numbers to S. Okay, so that's the definition of what a countable set is. So suppose we have a set A and we have a set B, and we say that there is a bijection from the set A to set B. Now what can you, so bijection. So what can you say?
One-to-one mapping from A to B.
Yes. So what can you say about the relation between cardinality of A and cardinality of
The
B.
cardinality will be equal because of every single element gets mapped.
Exactly. So is this clear to everyone else? Okay, great.
Yeah.
So basically, a countably infinite set will have the same cardinality as the set of natural numbers, since there exists a bijection. Okay, now let's look at two sets. Suppose we have n, the set of natural numbers. And suppose we have a set, say B, which is all multiples of 2. Okay, let's say all multiples of 5. So we have 5, 10, 15, 20, 25, so on. So what can you say about the cardinality of n and cardinality of B?
It will be same as cardinality of base. Same.
Could you repeat please?
Cardinality of B equal to cardinality of n.
N,
Since B
okay.
got infinity.
The cardinality of B is a subset of that of n.
Subset of n. So you're saying that the cardinality of B is less than n.
But the end limit
Goes to infinite. Then it
both
should
will be infinite.
Yes, it's infinite, but are there more elements in this set or this set?
In n, there are more elements in n.
So you're saying that there are more elements in n. And why is that?
Because B has all the numbers which are intervals. The elements of B are present in elements of n at intervals. That's why.
You
Okay.
couldn't say anything about the elements because both end in positive infinity.
Yes, they're both I mean, the cardinality of both of them are infinity, but you can, it's actually funny. You can say that they actually have the same cardinality. Because as we said, if we can establish a bijection from a set to the set of natural numbers, then both of them have the same cardinality. So now consider the function fx equal to 5x. Now let the domain of the function be n. Domain of f is n. Then what will be the range of the function? So the range of f,
So range, the other we have to tell the cardinality range or the numbers in the range.
that's the set. So the set in this case is b, right? So if we have 1, we get 5. So f of 1 is 5, f of 2 is 10, f of 3 is 15, and so on. So the range of f is b. So f is a function from n to b. N to b. Is this clear to everyone why the range of the function is b? Because all multiples are 5 over here.
And so
And
you
is
take the
this,
function as 5x.
yes. And is this function bijective? Okay, let's look at it individually. Is the function injective? What is the definition of injective? The definition of injective is if fx equals fy, that implies that x equals y. So in this case, y This means x equals y. So the function is injective. Now, is the function surjective? Surjective means that if we consider the codomain, every image has a p-image. Now, what is our codomain in this case? Our codomain is B. Our codomain is B. So, suppose the element x in B does not have a p-image. Now consider x by 5. Is x by 5 a natural number? X by 5 is obviously a natural number because B is the set of multiples of 5. Right. So basically, f inverse x in this case is x by 5. So if you take the element x in B, its pre-image will be x by 5, which is in the set of natural numbers. So we have a contradiction, and hence this is surjective as well. So we can say that this function is injective as well as surjective, which means there's a bijection, and hence the cardinality of n is equal to the cardinality of B. It is slightly counterintuitive because it looks like there are more elements in n than B. Right? If you take the set from 1 to 10, then we have 10 elements in n and we have only 2 elements in B. But since we can establish a bijection, we can say that both of them have the same cardinality. Now, what about the set n and z? So n is the set of natural numbers and z is the set of integers. What can you say about the cardinality of n and cardinality with respect to the cardinality of z? Anyone?
Is there a bijection again?
So what's the bijection in this case?
Let us define every element of n as ni and z as zi. So we get for zi equals to ni minus 1. So for every element of ni, for every I, we have one element in ni and the image in zi. So we can say it is a bijection.
Okay, so you are saying if we consider the element ni in n, then ni minus, then we consider we map it to ni minus 1 in z. Is that what you are saying?
Yes.
So for ni, so we are mapping ni to ni minus 1. So ni minus 1 in n, ni from n to ni minus 1 in z. Now consider minus 5 in the set z. Does it have a pre-image in n? So if you have minus 5 over here, it's getting mapped from minus 4, right? But minus 4 is not a natural number.
Sorry, I did a mistake. I thought z was whole numbers. I completely missed it.
Okay. Yes, so that's how you can establish a bijection from W to n. So whole numbers to natural numbers, minus 1.
Uh, can you establish a bijection such as this? Arrange set one, that is natural
Can you
numbers,
repeat the
in the
question once?
Okay, I'll repeat the question once. So we have the two sets, n and z. N is the set of natural numbers and z is the set of integers. So from minus whatever, -5, -4, -3, -2 up to positive infinity.
For
So
n, for we
And
arrange
what do
yes,
we have
n
to
as
do?
such. One, two.
what's the relation between the cardinality of n and the cardinality of z? That's the question.
We
And yeah,
arrange
continue with
n
your
as
solution.
we arrange n as such 1, 2, 3, 4, 5, dot dot dot, and
Okay.
z as such 0, -1, 1, -2. So on and on. Can we establish a bijection like that?
Okay. So what's your
Can it be
mapping?
like this? The cardinality of z equal to 2 into cardinality of n plus 1.
No, you can. I'll tell you that you can establish a bijection. So
One map,
basically, both of them
one map,
have the same
one
cardinality.
maps to
Yes.
0, one
One
maps to
map to
0,
zero.
2 to -1, 3 to 1,
Okay.
4 to -2,
Okay.
5 to 2, and 6 to -3, 7 to 3, so and so
Okay.
on.
Yeah. Yes. Yes. So how do you formally define this?
Each odd number in a set of natural numbers maps to x -1 whole by 2, and each even number maps to
Can we use the greatest integer function or the float function?
क्या बात है भाई लोग
and each even number maps to minus x by 2, like minus that even number.
Ahir Dada, if you are saying anything, we can't hear and neither can we see your video.
My phone just due to overheating.
Yeah.
This has been continue. All of you guys can see the whole board.
Yes.
Okay. So, did anyone have a formal solution to this?
No.
Any hint, Dada? Any hint, Dada?
Yes, you were on the right track. So you just need to state it more formally.
Can we say ni? Sorry, zi equals to greatest integer of ni by 2 into minus 1 to the ni.
Okay. Sounds a bit complicated. Could you repeat it? So Zi.
Equals to greatest integer of ni by 2
So Ni by 2. Yes.
into minus 1 to the n.
Into minus 1 to the power n.
Sorry, ni.
Yes, Ni. Okay, so if we have 1, you are mapping it to 0. If we have, so okay, so suppose you have a natural number of the form 2k. So for 2, 4, 6, 8 in natural numbers, they are getting mapped to, it's getting mapped to 1, 2, 3 and so on. And if you take the natural numbers 1, 3, 5, 7 and so on, it's getting mapped to 0, minus 1, minus 2. So basically it's a more formal version of what Ayush was saying. And yes, it will work perfectly. So for those of you who didn't understand, we do it like this. So suppose we take all the odd natural numbers. So we have 1, 3, 5, 7, dot, dot, dot. So we take these natural numbers. So we'll denote this by n0. So we'll map these to the non-negative integers. So we'll denote this by z plus 0. So we'll map this to 0, 1, 2, 3, 4 and so on. And we'll take the even natural numbers. So we have 2, 4, 6, 8 dot dot dot, and we'll map it to z minus. So that's minus 1, minus 2, minus 3, minus 4 and so on. So basically what you can do over here is, so our map is, if n is of the form 2n minus 1, where n is a natural number, then we map it to n minus 1. Does that make sense? So if we take 1, we are mapping it to 0. If we take n equals to 2, then we are mapping 3 to 1. If we take n equals 5, if we take n equals 3 over here, then we are mapping 5 to 2 and so on. So this is one map. and the other map is, suppose n is of the form 2n. So if n is of the form 2n, then we are mapping it to minus of n. Okay, so now take n equal to 1 over here. So you are mapping 2 to minus 1. Take n equal to 2 over here. So you are mapping 4 to minus 2, and so on. So basically, if you take both of these, then you can establish a bijection from the set of natural numbers to the set of integers. So is the relation clear to you guys? And this was a more elegant map actually. So if you take zi equals greatest integer function of ni by 2 into minus 1 to the power ni, this is a more elegant sort of a map. But
This map
both of these
works
are actually
for both of the
equivalent.
cases.
Could you repeat?
This map works for any and no both, right?
Yes. So it's just a bijection actually. So we are saying that basically we are saying that the set Z is countable. So it has a bijection from N. So therefore Z is countably infinite. Okay, now what can you say about the set R? What can you say about the set R with respect to natural numbers? Is R countable? Is R uncountable? R is obviously infinite, right? It's not a finite set. So what can you say about cardinality of R with respect to cardinality of N?
I think cardinality of R is greater.
Okay. And why so? Could you, so you're saying that the cardinality of R is more. So you're basically saying that R is an uncountably infinite set, right?
Yes.
Okay, so can you prove that?
Can you repeat the question again?
Okay. Prove that R is uncountable. So basically, prove that you can't establish a bijection from the set R to the set N. Acha, we'll take maybe 20 more minutes.
Is there anything to be said
R is a
about the
rational numbers are like wait, R is real numbers, right?
Real numbers, yes. Rational numbers we denote by Q.
अच्छा then तो
Yeah, I
Oh,
thought
two
R to be a random set. Sorry.
Can I try once?
Yes, go ahead.
Okay, say we have Ri as an element of R. So we just define for the moment Ri equals to 1 by Ni. So we have just a bijection 1 by.
Okay. We have a by.
I
Okay,
think
So we have bijection between rational numbers from 0 and 1. So, but we have
yes.
even more sections,
no,
infinitely
now
more
we have a
sections.
budget
So
between 0 and 1. Wait, I think I have a vote. Suppose let there be a set of real number. Let us say that we can form a countable set of real numbers. With the
Okay.
first number being something like 1.1345, second number 2.5678. Now let us construct a new number such that the first and the first digit is the first digit of the new number is different from the first digit of the first number in the set. Then the second
Okay.
digit of the new number is different from the second digit of the second number in the set, and we continue
Okay.
doing it so on and so on. Since at least
Exactly.
at least
It's
one digit
different number. Yes. Yes. Right.
from every real number, we have formed a new real number, thus contradiction.
Yes. Great. So that's basically a kind of Cantor's diagonal argument, and we'll do a formal proof of this. So we won't prove that the set R is uncountable. We'll just prove that this set is uncountable. So 0 to 1. If we can prove
Okay,
that
then
this
you
is
will prove
uncountable,
that this set belongs to R, so that will be infinite.
yes. So there's a property of uncountable set. So suppose X is an uncountable set.
Your video
So
went
if,
off.
okay, I'll switch it on here. Okay, so if X is an uncountable set and X is a subset of Y, then Y is uncountable as well. So since this interval is a subset of R, if we can prove that this is uncountable, then we'll have proof that R is uncountable. Now suppose that this consists of, say, A1, A2, A3, an. Now we'll write all of these in binary. So if we write A1 in binary, we get something like A1 is equal to 0. Say D1, D2, D3, D4, so on. Where D1, D2, D3, D4 are either 0 or 1. Now define AI as 0.di1, di2, di3, di4, di Okay, so where did the last class stop? শোনা যাচ্ছে তো নাকি?
Yes, Dada.
Okay, so where did we stop in the last meeting?
Dada, we just stopped at you were declaring AI.
Okay, I was declaring AI. Okay, so I'll just repeat this. It's not very tough. So we take A1, A2, A3 up to AN, and we write all of them in binary form. So suppose A1 is equal to 0.A11, A12, A13 dot dot dot. A2 is equal to 0.A21, A22, A23 and so on. A3 is equal to 0.A31, A32, A33 and so on, and AI is equal to 0.AI1, AI2, AI3 and so on. Now we define, okay, why did I write A over here? We have A over here already, so write this as D. Sorry. So A1 is 0.D11, D12, D13 and so on. A2 is 0.D21, D22, D23 and so on. And where all of these are either 0 or 1 because this is in binary. Now define EI, define E1 as 1 minus D11. Define E2 as 1 minus D22. Similarly, define EI as 1 minus DII. So if D11 is equal to 0, we have E1 equals 1. And if D11 is equal to 1, we have E1 equals 0. So we have D11 over here. We take E1 from here and we follow a diagonal path. So we take E2 as 1 minus D22. We take E3 as 1 minus D33. And so we follow kind of a diagonal path up to En is equal to 1 minus DNN. Now we construct a new number B, which is equal to 0.E1, E2, E3 and up to En. So is B equal to any number in this set? Okay, let's assume that there is a number in this set which is equal to B. Let this number be AK. So we are claiming that AK is equal to B. Now what is the kth digit of A from the left? So we have 0.DK1, DK2 up to say DKK and so on. But the kth place of B is EK, right? So the kth place of B is EK and EK is equal to 1 minus DKK. So AK cannot be equal to B and hence B will not be equal to any number in this set. So it's a new number. So B goes in here and thus, and so we can continue like this and hence this interval is uncountable. And since this interval is uncountable, we can say that this is a subset of the set of real numbers and hence RD is also uncountable. Was this clear to you guys? শোনা যাচ্ছে তো? কিরে শোনা যাচ্ছে?
Yes, Dada.
Okay, great. So you understood this proof?
Yes, Dada.
Great. So we call it Cantor's diagonal argument. You can read up about this later on. So we call this Cantor's diagonal argument. Okay, so I'll leave this proof to you guys. Okay, not proof. Establish a bijection from n to q plus and then n to q. So q plus is the set of positive rational numbers. So establish a bijection from the set of natural numbers to the set of positive rational numbers, and after that establish a bijection from the set of natural numbers to the set of rational numbers.
So can this
So
for n to q
yes.
plus, can we do it in the same way as we did this one?
No, R is uncountable, but the set of rational numbers is countable. Okay, we'll prove that the set of rational numbers is countable now. But I leave this proof to you guys. N to q plus bijection and n to q bijection. The only hint I'll give you is, suppose you have an axis like this and you plot the natural numbers like 1, 2, 3, 4, so on, and you plot 1, 2, 3, and so on. Now let this axis be the numerator and let this axis be the denominator. So you can write any rational number in a p by q form, right? So suppose take the rational number 1 by 3. So the numerator in that case is 1 and the denominator is 3. So you can denote it by connecting 3 over here and 1 over here. So this is just a hint to push you in the right direction. I'll leave this proof to you guys. You can discuss this later on. Okay, so this proof is pretty easy. Q is countable. So we'll express each rational number as a by b, where it is in its simplest form, where GCD of a comma b is 1. So basically the fraction is in its simplest form. Now define the function f a comma b as mod a plus mod b. Now take f a comma b equal to 1. So how many such rational numbers are there? So technically you have 0 by 1. So 0 is the only rational number kind of which satisfies this. If you have say f a comma b is equal to 2, then you have 1 by 1, 0 by 2, 1 by 1. So it's, and the negative ones as well. So you have minus 1 by 1. Yes, that's the only one. So you can proceed like this, and it's easy to see that if f of a comma b is equal to n, then there are only finite combinations of such a and b, and therefore it's a countable set. because there are finite such possibilities. So you can count them. Okay, so there's a lot of stuff that you can do with cardinality, but we'll stop with this topic for now.
Maybe you can
So
send us topics related to this on the WhatsApp group.
Yes, I'll definitely do that. So basically, recapping set is a mathematical structure, and sets are useful in almost every sphere of math, be it combinatoric, algebra, number theory, anything. So this is the first this is the first flavor of actual proper math that you get in school. So a set is also governed by certain laws, without which it doesn't hold, without which it is not consistent. So if you have, okay, so consistent. We say that a formal axiomatic structure is consistent if it is free of contradictions. So the naive set theory developed by Cantor and Dedekind was obviously not consistent because Russell's paradox was a contradiction in it. After which came the Zermelo-Frenkel with axiom of choice set theory, which is consistent. So it is based on certain axioms, right? Just like laws. So the without laws there would be total anarchy, right? So India has the constitution, so without which we would have complete chaos.
So
Similarly,
that
yes,
formula Frankel that the set theory free of contradiction without the axiom of choice.
yes, it is a consistent system. So basically, ZFC. So this is the set theory which we generally use. So ZFC is consistent and it is based on certain axioms. So you have, I think, 9 axioms. You have like axiom of extensionality, you have axiom of regularity, schema of specification, and certain. You have well ordering principle, that is the 9th axiom, I think, axiom of infinity power set, and so on. So basically, it is based on these axioms. So if you remove any of these axioms, the entire structure crumbles. So we'll discuss another mathematical system, which is the number system, later on a bit. So marker. Okay, so number systems. So before we get into number theory, we'll just establish a brief structure. So how did this system come to be? And the foundation of this system are the Peano-Dedekind axioms. So the number system rests on these axioms. So what do these state? Okay, before we get into piano axioms, I'd like to talk about this function. So how many of you know what this function is? Sn.
Success.
Yes, this is the successor function. So yes, the successor function, we define this as
S
Sn
of 2
equal
will
to
be
yes. So we define it as Sn equals n plus 1. And you know,
yes, Sahil that
because
discussed
this
the
function.
basics in the first class of that inequality.
Okay. So did he discuss the piano axiom?
In a nutshell,
Okay, so he said, okay, I'll just repeat it once before we get into number theory from next class onward. So he said that 0 is a natural number. So yes, this sounds a bit weird because we don't usually consider 0 to be a natural number. Now, equality cases. So this is an equality relation. So we have for every natural number x, for every natural number x, we have x equals x, and we call this reflexive, right? So equality is reflexive. We also have x equals y implies y equals x. So this is symmetric. This is reflexive. This is symmetric. And x equal to y equal to z implies x equals to z. So we denote this by transitive. So this is reflexive, symmetric, as well as transitive. Do you guys know what you call something which is reflexive, symmetric, and transitive?
Dada, can you repeat?
So what do you call a relation which is reflexive, symmetric, and transitive?
Your video went off again.
Acha. Yeah, it went up. Okay, so we basically say that such a
Actually,
relation is an equivalence relation. So an equivalence relation is something, which is reflexive, symmetric, as well as transitive. So we have x equals x, which is reflexive. X equal to y implies y equals x. So this is symmetric. X equals y and y equals z implies x is equal to z. So this is a transitive property. So all these three together constitute an equivalence relation. So equality is an equivalence relation. You can see from here. Now we'll move on to the next few axioms, which involve the successor function.
but yeah, as you know, that this piano denied the fact that the natural numbers are a gift from the god. That yeah, right now.
Yes, I think so.
But for zero is a natural number, but this is suppose like a gift from God. Then isn't he contradicting himself?
Yes, kind of. Piano actually said that started from 1 actually. He said that 1 was the first natural number and then he applied the axioms. But since 0 is the additive identity, we start from 0. So our next few properties are, suppose, suppose n is a natural number, then Sn is a natural number as well. Then we have Sn is injective. Can you say why? The successor function is injective.
Because every image has only one pre-image only.
Yes.
Because if it is two, it
the-
will always be one only. If the two is the image, one will always be the pre-image.
Yes, that's right. So if you have Sm equals to Sn, that means m plus 1 is equals to n plus 1, implies m equals n. So the successor function is injective. And so this was our what, sixth property, this was our seventh property. Oh, fifth property I think I missed. This is 6 and 7, right? So fifth property I'll write below. If p is a natural number, and a is equals to b, then a is a natural number as well. So if b is a natural number and a is equal to b, then a is a natural number as well. And our eighth axiom is, for every natural number n, Sn is not equal to 0. So this is 8. And 9, we have the induction axiom. So what is the induction axiom? So suppose you have a set K. Set K where, so suppose 0 is in K, if n is in K, then Sn is in K as well. So we can conclude that K is the set of natural numbers. So these are the basically 9 statements. So these sound pretty simple and kind of trivial, but without these, the entire structure would have crumbled. So it's pretty fascinating in that way. So what is addition? A plus, suppose you have A plus B. Addition is basically recursive. So suppose you have A plus S of B. Suppose you have A plus S of B. This is equal to S of A plus B. Now what is B? B is S of B minus 1. So this is S of A plus S of B minus 1. What is this? This is S of A plus B minus 1. So basically, can you see how it's becoming recursive? Let's take a shorter example. So suppose you have A plus 3. A plus 3 is equal to A plus S of 2. What is A plus S of 2? This is equal to S of A plus 2. What is 2? 2 is S of 1. So we have A plus S of 1. What is A plus S of 1? It is S of A plus 1. So we have S of A plus 1. What is 1? 1 is S0. So we have S of A plus S0. How many brackets? 2 brackets right here. What is A plus S0? It is S of A plus 0. This is A. S of A. So basically this is a recursive function. So if you compute this, you get A plus 1, A plus 2, A plus 3. So addition is basically recursive, and same for multiplication. So suppose you have A into S of B. So what is this? This is A plus A into S of B minus 1. So this is A plus A into S of B minus 2, and so on and so forth until you get A plus A dot 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 S of B times. So these are both recursive in a way. So this is basically how you define a system. Now, so this system, like any other mathematical system, is based on certain axioms. Now, we say that a system is complete if every property which holds true in the system can be derived from its axioms. So we say that a formal axiomatic system is complete if every property which holds true in this system can be derived from the axioms of the system. Now, this Austro-Hungarian guy called Kurt Gödel, in 1931, he said he came up with this theory. I'll write this below. So he came up with this theory, which is known as Gödel's incompleteness theorem. Incompleteness theorem. So in 1931, this 25-year-old guy came and absolutely shook up the world of mathematics with his incompleteness theorem, which basically said that a formal axiomatic system cannot be simultaneously complete as well as consistent. So basically, I mean, it's a fascinating theory actually. You can read up more about this, but it's already 8:20, so I won't go beyond this. You can read up more about this. It's a completely fascinating theory. So basically, this crushed all hopes of a kind of theory of everything in mathematics, because the system cannot be complete and consistent both. So we'll end today's session here. I don't think we took more than 1 hour and 15 minutes. So that's good. So does anyone have any questions